hear me and see my screen?
Yes.
Yes. Okay. Today we'll continue with investigations of tensors. And so we found yesterday some rule of rising of the tensor index. And what I would like to tell you also. So, okay, I just will see what we did. Okay, so just to again to remind that we speak now about metric tensor, and just to want to remind, today we will see some example that metric tensor GIK. In principle, this metric tensor again has information about coordinate system. So, and this we can write. I put this parenthesis, but in principle it's not so important. So this is scalar product of EI and EK. Okay. So if you have some reference system, coordinate system with where EI and EK, this is basis vectors. Okay, so to finalize about some rules of with which we can work with a tensor, and after this we again speak about metric tensor. So we can write the rules of rising, lowering, indexes. So which is what it means. For example, we can make a operation with the tensors to do something with the tensor, but finally we again obtain tensor. So, for example, if I have, and we not yesterday, on Friday, we received some already the rule, and we proved it. The rule which tell us how we can make an index low when we have an index higher. So I will repeat it here. So, for example, if we have tensor A, let's put index I below. So, and if I will multiply on the metric tensor IK, we can see that that I, this is summation index, and W index. So in the left part, we will obtain AK. In our languages, we sometimes use, but not in English, use like we call such a kind of index K. We call in this case K. We call speaking index. So it means that this index tells us which index should be kept from the left side in this case. So we tell us that from the right side we can see that summation index I, and this index will disappear in the left part. So but K will be kept. So this is rule of rising. This is rising. If I have otherwise, I have A I, so index above, upper index. I will put here G, I, K, and finally I will obtain A, K. So we make index K below. And this is the main one of the main operation. The same we can make, for example, for a tensor of, so this is for tensor of the first rank, and for the vectors, and for the tensor of second rank, we can do a similar way. For example, we have let's put here LM. I will put here GMK. So on the left part, again, M, this is summation index. I will have A, K, L. And so we can see that we had a tensor with mixed indexes, but finally we obtained contravariant component from the mixed component. Here again, here you can see that we obtain from contravariant component vector to we move to the covariant. Here otherwise. Oh, this is procedure. So, for example, I can do from this vector tensor A. I want to keep the same index on the left, for example, ML, GM, K, and from the left I will have A, K, L. So I made a covariant tensor from mixed tensor. There is also the procedure swapping of indexes. So it means that, as an example, we have, for example, if we have some tensor of the second rank, but if we will consider the same indexes, so I just put K equal I, what it means? It means, again, we remember that it's a sum by E by I. So it will just scalar. We can do the same with a tensor of any rank. So for example, I have A, R, K, M, L, but I can do operation if I want to obtain the swapping of the tensor. I will put M, for example, M equal I, and it will be I, K, I, L. So I will obtain the tensor of the second rank. So this is a trick. Not trick. This is operation. We can multiply tensor. We can consider summation of them, and in principle, and it can be proved that finally, and in principle, it's understandable from here, that if you will write the transformation of the tensor of final object from one coordinate system to another, you will see that it's really behavior like a tensor. So, and the object which we obtain here from the left part, this is also tensor. And transform as the tensor of the first or second rank correspondingly. Okay, I also, what I want to add about metric tensor, that in principle, we can prove that metric tensor, he behaves like a tensor. So, for example, we can consider the small, consider dx k, and let's consider how this component, in this case, is tensor of the first rank, this is a vector, transform from one reference system, coordinate system, to another. So again, from prime to, let's consider this different system, prime to just not prime. Okay. X prime to x. Okay. In this case, I can write again the x k prime equal. So, and we understand that this, since we have some transformation rule from one system to another system, or rule, this is just a mathematical analysis. So I write this is the x k prime. So, but we have relationships between coordinate axis by the xi, the xi. So, by definition, the basis vectors, they are also transformed from one coordinate system to another. So we can write for the, and we will see an example a little bit later. So a e k prime, I can write that this is dxi by dx k prime ei. If now we will write the expression for metric tensor k prime, okay, L prime, so this is scalar product a k prime e L prime, and now I just put here all these expressions, so it will be dx, so I prime, so I put for the low index. It's understandable that I can okay, I think it's better to write this. I will also dk prime like this. So it will be dx. Doesn't matter with I'll consider COI or counter-variant component, okay? The xi okay. So now if we will consider what is a metric now, let's consider what is a metric tensor in a prime reference system, G k prime, L prime, I can write. So this is E k prime, E L prime, okay. I will not, I will omit this. So if I write like this, it's understandable that this is scalar product. So I will not use this parentheses. And we use these expressions. This one. So it means that I need to write the xi, the xk prime. I will put nearby the second derivation, so the term, the multiplier, which is related with the second basis vector. So in this case, the xm, the xl prime, and after this I put ei, e, since I put here m, I put here m. Okay, so I have finally that this is the xi, the x prime, the xm, the xl prime, gem. So we can see that really we proved that metric tensor transformed from one coordinate system to another as a tensor of the second rank. The same you can repeat for this I made for covariant metric tensor. Twice, we call it sometimes twice covariant tensor. And you can do the same for contravariant metric tensor. So this is proof that this tensor is transformed as a tensor. Okay, now I want to we can look on some examples, and for example, Cartesian system. If you have some vector, some element of length, it's a vector. So let's put, okay, seconds. I just put coordinate net. And it looks like 2D I can, so just a second, put it 3D like this. I'm not sure this is much more understandable. So we consider three-dimensional space with x, y, y, z, and we have some vector in this. Let's put it this one. It's a big, but let's consider that we consider the element of this vector. Okay, so yeah, and this vector has a corresponding coordinates. So, and I want to write examples. First, Cartesian system. And I want to write the element of length of this vector. It's much more convenient to write the square of element of length element. So I'll write dl square, and here I consider, as you understand, three-dimensional. And what is this? This is a generalized rule of Pythagore theorem. So I can write x square plus dy square plus dz square. And if we will represent this, when I put equal in a circle, it means that I continue, because in the previous lectures there was some misunderstanding. So if I will write the same, like g I k the xi, the x K, I can see that the component of the metric tensor is this one. As we discussed, it's a table, and the component of metric tensor is a constant in this case. 1, 0, 0, 0, 1, 0, 0, 0, 1. So we have only diagonal elements, and sometimes I will write it like this. So which is the same, okay? Just not to repeat 6 times or even more zeros. So it means that we have only diagonal elements. And for this case, we can I can write that G(I)K) equal just a 3-unit tensor. So the next, if we, for example, consider Minkowski space, so this is special relativity, space in special relativity. From the point of the space, it's a flat, and time, and we have also time, so that we need to write the square equal c square dt square minus the x square minus the y square minus the z square. Again, if we will represent this in general case like this, so we understand that I will write another case, that G, and usually, but I will not keep this rule, because in foreign literature, the people like to use, as soon as they put Latin indexes, you understand that this is 3-dimensional space. If you put Greek indexes, it means that this is 4-dimensional case. So in this case, I need to write alpha, beta. It doesn't matter, you understand, it's not so important. It's just an agreement. And this is exactly opposite to the case which of notation which was used by Landau and Lifshitz. So since we have our grade school of Landau, we are common to use not a Greek but for space, but Latin indexes. And for Greek, we remark otherwise the 3-dimensional space. So, but it's just how it is convenient for you or for somebody else. So this is not something very important from the point of using of mathematics. So, for example, now now I will keep here Latin indexes, but I will tell that now here, not here, here I will put above here I equal 1, 2, 3, and here, because now we are working in principle much more with mathematics, so it's not so important. And here I put 0, 1, 2, 3. So 0, this is for time. It means that if I will put as a coordinate x0, this is even not t. C multiply on t, where C, this is speed of light. Okay, and if we will multiply speed of light on time, we exactly obtain the scale of the length, which should be in the interval, and we call it interval. I mean this one. So, and x1, this is x, x2, this is y, x3, this is z. For metric tensor, we have a non-zero component of the metric tensor. G0, 0 equal 1, G1, 1 equal minus 1, G2, 2 equal minus 1, and G3, 3 equal minus 1. So the component of the metric tensor 1, minus 1, minus 1, minus 1. And here I will put others component as 0. Also, there is already I touched this point that sometimes people like to use the metric with a different signature. For example, to put minus in front of the time component. So like we'll put the red minus, and in this case plus, plus, plus. So you can also see like this, but for me it is not convenient, and for our school, so we are using signature. I put here as a form. So this is an example, and this is for special, so special general, also special relativity. Now to feel what is how it is working for the reference system, we can consider, for example, again, no, I would like to ask you a question. Or maybe later. Okay. So now, so much more in detail we'll consider polar coordinates. Are you here? Can you hear me? Hello,
Yes,
can you
we are
hear me?
here. Yes, yes, indeed.
Okay, fine. Because no any noise and okay. Once I continued to give lectures and the connection disappeared, and I spent like 5-7 minutes. Finally, students reached me and said that something wrong with internet. So sometimes I will check that you are present. So let's consider a polar coordinate system. It means that in polar coordinate system, so we have x, y, but in polar coordinate system, if we have some point, so we are using r and so if we have, I will put here vector, r vector, so I can represent this vector in general case if this is ex, here unit vector ey, we can represent it as x ey plus y ex. I wrote some stupid things. I don't know why. Of course, this is also y. Okay. So, and we have a transformation from one reference system to another. So coordinate, our coordinates are changed like this, which you know very well. This is r cosinus theta, y r sinus theta. From this, I understand that I can represent vector r as r cosinus theta, just put it here, ex plus r sinus theta ey. Okay. Now, by definition of basis vectors, we should put it here. This is transformation. So here I will write the basis vector. This is what? This is dr by the x I. So you can see it's just simple if you will consider the representation of the vector. And in this case, we can obtain ER, so it will be dr by dr. Let's look here. So it will be cosinus theta ex plus sinus theta ey. The component of, the basis vector e theta, it will be dr by d theta equal, so we again look on this one. I will have minus r sinus theta e by the polar coordinates. Of course, this is two-dimensional and understandable that we have it. So for more simple case, we can the same consider for three-dimensional, for the cylindrical coordinate or spherical. E x plus r cosinus theta ey. So, in principle, you can see that, so we can discover that e theta, for example, doesn't have a unit length. So it's not obviously that it has a unit length in another reference system, another coordinate system. So after this, let's consider what is dl square interval of the length. Okay, this is dr by dr. Some differential of this vector. So what we will have? We will have, I will put this one and this one. Okay, so it will be dr. In the first, I can consider this like dr on er. It's early to put it. Okay. Plus d theta e theta. So this is representation of the vector in polar reference system. Because this is Cartesian, I put here Cartesian and polar, the same vector will be, okay, it's better not, doesn't matter. So let's continue, otherwise we will put in a lot of detail, will be not in time. dr er plus d theta e theta. Okay. Oh, this one in square. So finally, what I have the first sum on square, dr square, er plus 2 dr d theta er e theta plus d theta e theta e theta. So in this case, we can see that in a polar system, we will have the following component of the metric tensor. So the RR. Sometimes we can, and it's useful to put as the indexes the same letter as a coordinate. So we of course could put here 1, 1. But this is the same, but it's much more convenient sometimes to put exactly the letter in the indexes which are related with coordinate. Just remind us with which coordinate is related this component of the tensor. Okay, it will be ER. Okay, scalar product. The component R theta this is this one. The component theta R e theta er, and the component G theta theta e theta e theta. So this is representation of the components and product of through the basis vector. We can check, for example, now that let's check that if that this is equal 1. Okay, let's check it. So I can check that if I will put here the basis vectors as product, what it will be? It will be I look here. So it will be cosinus theta ex plus sinus theta y. So in principle, I need to multiply on the same, but I can put it square. And what is important? So finally, since we will have cosinus theta square and multiply on, for example, ex, this scalar product will be 1. So, and I will not write it. Okay, I will keep it. Of course, the same will be with the sinus. So it will be sinus squared theta. Because it will be again EY multiply on EY, which is unity. On unity. And also I will have the mix product EX and EY, which is 0 for the Cartesian system. So finally I have this one and I have this one. So I just put here to remind that we used that EX on EX equal 1 unity and product EX EY equal EY EX, and this is 0. So exactly what we have for Cartesian system, because in Cartesian system our coordinate axis is perpendicular to each other. Okay. So we really proved this point that GRR in polar reference system equal unity. We can also see that ER on E theta. I understand that this is simple, so now we are working like with analytic geometry, but it's important that you could feel the notation and everything to understand. So in this case, if you will multiply this one, okay, so what you will have in this case, I will write in detail once, plus r sinus theta e y and minus r sinus theta e x plus r cosinus theta e y. Again, I will take into account all of this. And I will have only the summand where we repeat this multiplication EIX. So in this case, it will be minus R cosinus theta sinus theta plus, and from EI twice, I will have plus R sinus theta cosinus theta, so which is equal 0. So we proved that this non-diagonal element of the metric tensor, which is G R theta. You can put here G R equals 0. And finally, we can look what's happened with another diagonal element. So I'm making G theta theta, which is E theta multiplied on theta, which is equal. So we need to look here, this. So, and it means that, okay, it means that we need to write here minus R sinus theta E. Okay, EX plus R cosinus theta EY. Please follow for me because I can, if I will make some mistake, I hope that you will see it and tell me. So what it will be R square sinus theta, because again we will have only EX multiplying EX. And from the second, I will have summoned R square, here also square, okay, cosinus square theta. So finally we will have R square. And it means that G theta theta equal R square. So what we finally have? We have that in polar coordinate system, the component of metric tensor is following. This is 1, because this is GRR, R square, 0, 0. So this is example with a polar coordinate system. For example, I can, of course, we can consider, this is the point when we can ask the question. How do you think if we have a cylinder and we are on the surface of this cylinder? In this case, the curvature, where this space on the surface, I mean, the surface of cylinder, so 2 dimension. The surface is curved or not? This question to you. Are you here?
Yes, here.
Please give me your suggestion. This is curved space, curved surface, or flat surface.
Well, I think that it's curved surface. However, maybe if we is in a cylindrical system of coordinates, we can suggest that it is flat surface. That's kind of.
Okay, somebody else. For example, Denis Fedonenko.
Here.
Denis.
Here. I'm here.
Ah, you're here. Okay, Dennis, maybe. Denis. I correct pronounce your name?
Yes.
Fine. What is your opinion? Is a curve or flat space? And justify, please.
I don't understand words in English.
So it means this is the surface, the flat plus key curve, not
Плоская или сферическая?
no, или кривая. Плоская или кривая?
Кривая.
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 Okay. Семен Каноненко.
So I already tell my opinion about this case.
I'm sorry because I don't see you now. I would like a little bit to speak with you. I mean with the students. Фандеев Артем.
Yes.
What is your opinion? Flat or curved?
Please, можете repeat.
So the equations that we have cylinder, cylinder surface, цилиндричная поверхня, okay? Yes. And the equation, this surface поверхня, it's a flat or curved? Плоская или кривая?
Наверное, кривая.
Okay, and last one. Sometimes I will do it because I would like to be sure that you are not sleeping, but Олена. We have only one Olena. Olena Chikina. Are you here? Lena don't care about. Okay. Somebody decided to leave lecture due to these questions. Don't be scared. It's okay. I can ask questions. You can answer. You can answer not right. If you don't understand in English some words, please ask me to tell, to translate something or to repeat. Be more active. So, okay. Okay, now the right answer. So, all of you are not right. The surface of cylinder is flat. And to check it and to prove it, it's very simple to prove it. Just need to take the paper.
So in which system of coordinates it is flat?
No, the curvature of the space doesn't depend on the coordinate system. This question was very important, which you asked.
No, however, we can choose some part of this surface, and it will have curvature radius, and it will not be zero, as it must be for.
No, we didn't.
Or it's not the definition of flat surface. No, curvature radius. Radius. If it's zero, we can say that the surface is flat, or it's not a definition.
In the first R shouldn't be zero, because if you will consider the simpler representation which I gave you as a Gaussian curvature, which is not full, it's just, as you remember, I put like this, proportional, and which divide of two main radius if they exist, of course. So, and for the flat space, this main radius tends to infinity. Why the curvature, Gaussian curvature, equals zero. So
okay. Yes, I'm sorry.
The first. The point that, and you need to remember that the curve, I will put it, curvature, if some student doesn't understand English well, so curvature, this is кривизна. Okay, please write in your conspect. Curvature is a previous. So, and curvature is something which is not changed due to going from one reference system to another reference system. We will see it later. This is some scalar. And as you understand that if you speak about scalar, a scalar doesn't change when we go from one coordinate system to another coordinate system. So this is a point, very important. About cylinder surface, the point that how you can check this is, and again, you made some, not a mistake, but some misunderstanding, because yes, for example, the component of metric tensor can be different from one, but it doesn't mean that the space is curved. So because you can apply some transformation, and if you using this transformation, you will move to flat space, it means that space can be flat. So this is the point, the first. The second, which is a much more simple representation just by hands that this surface is not curved, because if you can, how you can make a cylinder. So you take paper, okay, and you just hold it such a way that finally you obtain the cylinder. I will put like this. So, okay, you hold it like this. So it means that you can again open this paper such a way that from cylinder surface you will obtain flat surface. Okay, it's understandable. So you just hold it at all, and on cylinder surface is a flat surface. Of course, there is a point that there is such a things that of course we need to cut it and to open. So if this is if we will consider that there is some line here, yes, and we can't move from this part to this part. So in this case, it's completely bad. Otherwise, if there is no any here, how call it, this line when we connect left part with right part, so we have some cut. And in principle, yes, it's looking like you can there is a part of a spherical surface that you can walk around without any problems. So it looks like a circle. So, and in principle, intuitively, we can put the definition such a way that a surface is curved when it can be decomposed into a plane without extension and cuts. Please write in your conspect. The surface is curved when it can be decomposed into a plane without extensions and cuts. What is extension? What an extension? So it's, for example, if we have really spherical geometry, so, and I put here 4. Okay, sphere. So, and when we consider like this, and so what we you know very well that when we look on the globe map and it looks like this one, okay, this equator, and this is, so you can see that you can't distribute this surface of the sphere on your table without any stretching. And this tell you that the surface is curved, very curved. So this is like an intuitive point of this. And in principle, if we will consider on element, so in spherical reference system, let's consider here you can chop spherical reference system, coordinate system. which is, I will remind, this is X, Y, Z, and in the system we have angle, let's put it phi, theta, and r, okay? So, and we will have, in this case, the element of length, the L square. So the transformation between coordinates, this is R. So Z, Z, this is R cosinus theta, okay? This is sinus theta cosinus phi, and Y, this is R sinus theta sinus phi. So this part, we need to project this on the plane xy, and after this, so, and finally the element of the length square, and you can prove again if you will put this in the x square plus dy square plus dz square, you will finally obtain very famous expression which you used many times, I'm sure. F square. So again, if we will put the component of metric tensor, we again see that this is only diagonal elements, and G11, GRR equal which value? Please tell me.
1.
1. G theta theta.
R square.
Yeah, square.
R square. And G phi phi.
No, it must be maybe R in fourth grade. Or, I'm sorry. Also R squared, sine squared also.
Right. So this is component of the metric tensor. In this case, so this is an example. These are the examples which we consider it, and you can apply it to any reference system which you would like, and to train if you would like. So I can write that for this case, the Gaussian curvature is not cos zero. Okay. Later, we will discover that in general relativity we will come in some object which we call scalar curvature, and it will be in Einstein equation. So, and again, curvature doesn't change when we go from one reference system to another. One point that, for example, of course, we will use this trick if we will have some curve space, we can choose some very small scale and consider that in this scale, for example, we can consider in the vicinity of this point, the space is a flat, as usual, when we are trying to simplify something. So we sometimes, by the way, this such a kind of system. I mean, when we used this trick, it's called Galilean coordinate system. Galilean reference system is better in this case to use. So it means that we come back, it's just for memories, that we come back in such a flat of space. In principle, we come back in the situation when, from the point of an Einstein experiment, Gedanken experiment, in the case when elevator falling down, free down, and we don't have any forces, and as an example, any curvature. But this is, we will consider this, we should be very careful. So we'll consider this later and we will use it, but for special things. I also would like to mention, to finalize this lecture about tensors, because we need to finish it in 8 minutes, right?
Right. Right.
Good. So I want to finalize, and please write it in your conspect. And again, I say that I will check your conspect and how you are working with your conspect, not just listen, but if you something don't understand, you can translate it like this. So the idea about tensor also, very important, that if we can write in some equation between quantity which is measured locally, it doesn't matter, but it's important in principle. So it means that if we can write some equations in tensor form, and it means, and we are sure that this equation is true in this coordinate system. Due to the fact that we wrote it in tensor form, it means that this equation is true in all coordinate systems. So again, I will repeat. If you have some equation which is true and represent in tensor form in one coordinate system, it means that this equation is true in all coordinate systems. So now you can feel this importance and beauty of the tensors, because this possibility to generalize the equation for all coordinate systems, this is really important point. And it should be like this. You can say, of course, it can be strange that something work in one reference system and doesn't work coordinate, doesn't work in other coordinate system. And I agree with you completely. And it was a problem. Again, I want to repeat that the special relativity, which is working with inertial reference system, which is special reference system, it was really the problem that this doesn't work in all reference system. Why? Again, the general relativity should appear to obtain the general solution of this problem. So, okay, for now, which are related with tensors, it looks enough to go to the next point, very important, which we will consider in the next lecture. This is covariant derivation. It's one of the equation. If we can see that if we have a curved space, so we can see that operation with the object became, the mathematical object became not so, how call it, однозначно, okay? So it means that we also can understand that the operation of different to obtain the derivation is also can be different from the same in flat space. And this we will consider why we need this operation. Because our final goal to obtain the equation of gravitational field. And as we remember, so if, Poisson equation, we have Laplacian. So we have a second derivation of the potential. And we understand that, of course, if we speak about equation of gravity, we need to have corresponding operation. As a result, we will obtain such a new object, which call Christoffel symbols. So if you have a question, please ask. If not, we can finish for this, because it's not a point to start more complicated task just now, subject just now. I also want to say that now it's very important lectures, because if you will be not present on one of this lecture, which I now give, it will be really complicated to understand next one, because every next result will be based on the previous result, on the previous discovery. I need to make a snapshot. No questions?
No questions.
That's good. Not good, I don't know. And also, soon I will start to give you some home tasks, which I will take into account the final estimation of your knowledge and your work during semester. Okay, if you don't have any questions, so I wish you a good week, good days, and see you on Friday.
Thank you. Goodbye.
Looks goodbye.